Hey guys, welcome back. So in the last video we saw how to delete a node from AVL tree, whereby we saw that when we are deleting a node from AVL tree, there can be two conditions, that is a rotation is required and a rotation is not required. And we dealt with all of those conditions in the previous video. So hope the entire idea was clear. Now in this video, we will learn how to delete the entire AVL tree. So as you would have guessed, deletion of entire AVL tree is basically the same as what we have done in case of binary tree or binary search tree. That is, all that we do is we make the root as null. The rest of the node automatically gets deleted by garbage collector. So let's say this is our AVL tree, and if we want to delete this tree, what we do is we simply make the root as null. So once this node is made null or deleted, automatically this node and this node becomes orphan. So garbage collector deletes this node and deletes this node. Now after deleting these two nodes, automatically this node, this node, this node and this node, all the children of the previous deleted nodes becomes orphan once again. So garbage collector again deletes these nodes, and similarly this process goes on till each and every node of this tree is deleted. So that's how the entire tree can be deleted with only one single statement. Fine. Now let's see what is the time and space complexity of this algorithm. Since we are just assigning null to root, it is a constant time operation, so time complexity is order of 1. Space complexity will also be order of 1 because we are not using any space for doing this operation. So I hope you have understood how to delete the entire AVL tree using one single line. Now before we wrap up this AVL tree chapter, let's quickly see all the operations that we have seen till now for AVL tree and what was the time and space complexity of each and every operations. This will ensure that we will quickly do a revision of the entire chapter. So what we seen is, first we created a AVL tree which took time of order of 1, space was also order 1. Then we inserted a node in the AVL tree which took log n time and space was also log n. Then we deleted a node from a AVL tree. It took log n time, log n space. Searching a value took log of n time and log of n space. Traversing the entire tree took order of n time and order of n space. And finally, deleting the entire tree took order of 1 time and order 1 space. Now I would highly encourage to please pause this video now and see why each operation took that time complexity and that much space complexity. Please don't look back at the previous videos. Try to answer it right from this video. This will ensure that you have a quick recap of all the operations and their complexities involved. Fine. So I hope you have been able to answer which operation took which time and which space complexity and what was the reason behind it. Now let's quickly go to one more table whereby we are comparing binary search tree with an AVL tree. So when we started learning the AVL tree, we said that there are few problems which are associated with binary search tree. That is, it in the worst case can get little disbalanced, and because of that the performance of binary search tree starts going down. Hence we need a balanced binary search tree which is also called as AVL tree. So here if we do a comparison, we can see that creating a tree, either it is a binary search tree or an AVL tree, both of them took order of 1 time. So we were fine. But the main difference comes over here, here and here. That is, whenever we want to insert, delete or search a node in a binary search tree, in the worst case, it might take order of n time, because if the tree gets disbalanced, the height becomes too much and all of these 3 operations takes more time. But in case of an AVL tree, as we already saw, that it never allows the tree to get disbalanced at any stage. Hence, all of these 3 operations, even in the worst case, will take order log n time. Now traversing a tree of course will take order of n time in both the cases, because it does not depend if the tree is a balanced one or not balanced. We always have to traverse each and every node and it will take order of n time. Now deleting a tree, again since we delete only the root, it is constant time in both the cases. So the difference between binary search tree and AVL tree comes in only these 3 operations. So if somebody asks us why we should use an AVL tree and not a binary search tree, a simple answer is the worst case scenario for insert, delete and search, AVL always guarantees it to be order log n time, whereas in binary search tree it might go till order of n time. So we should be using AVL tree in those cases. Fine. So with that we come to end of AVL tree chapter. Now the code for all of these operations is available in the resource section. Please go and find it there. But I will highly encourage that since we have discussed all of these algorithms in lot of details, please try to implement it on your own in any of your favorite language. If you still face any problem, the code is available in Java. It is there in the resource section. Please have a look at it. So we will end this video over here, and with this we come to end of AVL tree chapter. In the next video, we'll pick up the next topic, that is heap. Thanks for your time. See you in the next video.